I will be presenting my findings of participating in all SemEval-2023 text-based tasks. It should be noted that this is a continuation of my work on the last year tasks, because I didn't manage to answer all my research questions there. So let's start with looking at multitask learning and natural language processing. Before the large language models, we used to carefully select tasks and carefully tune how we share the information across these tasks in our models. Now we commonly use a much easier way where we just have multiple decoder heads on top of the model and we have a shared encoder. A very recent development is this increasingly popular intermediate training. So let's take a look at what that looks like. So in this overview we can see on the left the very basic NLP setup. So we have a target task with the dataset, we train on it and we get our model. So the arrows indicate training here. Then roughly since Word2Vec we more often first train something on a very large set of raw data, a language model, and then we fine tune this on the target task data and then we get our final NLP target task model. And a more recent development is this intermediate training, where we take a language model that is trained on a large amount of raw data, and we train it on a variety of NLP tasks. And then from there we get a stronger starting point, so a language model that is fine-tuned towards NLP tasks. It should be noted that this has many names. In this presentation I will stick with intermediate task fine-tuning. So it should be noted that most work on this intermediate task fine-tuning is done with generative models. Most work on autoencoder models uses a carefully curated set of tasks. So then we only vary one of these dimensions and then we can see what the correlation of this is with performance. So this could be things like task type. Is there a transfer between sequence labeling and classification possible, or does it make more sense to stick within sequence labeling, for example? Or it could be across domains. Now, as opposed to this, I will also use autoencoder models, but I will use all SemEval-2023 text-based tasks as a proxy to an uncurated set of NLP datasets. So it would look more like this. It's just a variety of things, some of which will match in some dimensions and some of which won't, and there is no guarantee that all combinations are there. So during this research, I was aiming to answer all the following research questions. So first I wanted to investigate how useful intermediate task fine-tuning is for autoencoded language models in this varied setup. Then, is intermediate task fine-tuning also beneficial for a somewhat arbitrary set of tasks? And is the selection of the target or the source task more important to find a successful transfer? Does it matter if we train on a combination of datasets, or can we also train on single task to obtain this successful transfer? So maybe we just need to make a more careful selection. Then are dataset smoothing or heterogeneous batches beneficial for intermediate training in our setup, of course? Then we tried scaling up, so perhaps just the SemEval-2023 text-based task is insufficient, so I tried adding the 2022 task to see whether that had an improvement. And finally, I was interested in finding out which properties of datasets are good predictors for transferability. So this is an overview of all SemEval-2023 tasks that are text-based, and we can see from this table that there's a wide variety of tasks as well as task types. Furthermore, there's a wide variety of languages, although it's mainly English focused, and datasets have a wildly different sizes. So, and this probably correlates also with difficulty of the tasks. So these are our main results. Here on the y-axis we have the metric of each task, so notice that this is different for every set of bar plots. I know that this is incorrect, but this is the only way to visualize it nicely. And then we have our four models. So the single task baseline, the multitask model that we call retrain single, where we train on one single task and then transfer to another single task. Then we have the multitask model, so one model trained on all SemEval tasks. And then we have retrain all. And with retrain all, we take the multitask model and we fine-tune it again on the target task. Now, the main takeaway from this graph is that all of the models are the optimal one for some of the tasks. So it is very hard to see trends in here. I know there's also too many results to look at once, but it was very hard for me to find trends in the 2022 as well as in the 2023 submissions. So let's take a closer look at the results. So this is a confusion matrix with all our target tasks on the y-axis and all our source tasks on the x-axis. And on the x-axis you can see that it's longer than the y-axis, and that's because at the end we include the different setups when training on all datasets, as well as also adding the SemEval-2022 dataset. So the last 4 columns include the 2022 and the 2023 data. Now the first thing to observe from this confusion matrix is that I actually rounded up all colors to match the 0.0 point, and this means that there are many negative scores in here. So we shouldn't employ multitask learning if we are unsure whether we will gain a performance from it, because in most cases we actually lose performance. Then the next takeaway would be that we see more consistent gains on the rows instead of the columns. And this means that the selection of the target task is more important than the selection of the source task if we want a successful transfer. Finally, when we look at the last 8 columns, so these are the multitask retrained models, so the intermediate fine-tuning results, we don't see much more consistent gains compared to some of the single task results. So if we select carefully, we can do at least equally well compared to training on all and save a lot of compute. So when we look at our test results, we can see that we rank mostly in the intermediate level. For some tasks we do a bit better, for others we do a bit worse. But in general, this is not at all the focus of my submissions. I just wanted to answer all those research questions. So more interestingly, when we look at the correlations, we can actually try to find out which properties of a setup can predict a successful transfer. So what we did here is we looked at the difference in performance between the baseline and the multitask setup in all setups where we transfer from one task to another task, as we have already shown that is a successful or just as good as training on all, and it allowed for a more controlled experiment here. So let's go through these features. So first we have the baseline scores of the source and the target tasks. So we compare the score of the baseline of the source task to the gains that we observe on the multitask learning. So the gain is defined here as the multitask learning score minus the baseline score. If you look at these correlations, we can see that the baseline of the source task and the baseline of the target task are not good predictors, and neither is the ratio of these. This might be explained by the fact that the baseline scores are different metrics, right? So for each task we have a different type of metric, so calculating a correlation across these is a bit odd, perhaps even incorrect. Then we have the overlap in the task types. So here we look at whether the tasks are like sequence labeling, maybe they're span labeling or classification, and we try to find an overlap in these and use the ratio of overlap to predict performance, and we can see a slightly negative correlation. So this number is relatively small. I would not say it's a good predictor. Then we have the number of source languages, the number of target languages, and the overlap in languages. So here we would have the hypothesis that if there's a large overlap in languages, successful transfer should be easier. However, scores show that this is not really the case. Finally, we have the same with domain overlap, with also a low score. But then, interestingly, we arrive at the higher correlation scores, being source size and target size. Now, target size might be intuitive, right? Because if on the target size we don't have a lot of data, our baseline model would not perform very well, and it's a bit easier to gain improvements. So this is maybe a more universal way of measuring baseline performance compared to the actual baseline scores, because we have this difference in metrics. For the source size, this is perhaps a bit less intuitive, but my own hypothesis here is that on the source size, a smaller size is beneficial, because we don't need to learn the source task. We just need to get an intuition about the source task to find a better initialization for the target task. So this could be a nice venue for future work. Perhaps we should make all the source datasets smaller, so we don't learn too much. We don't learn them too much in detail, which is not useful for the target task at all. So then to sum up, for a non-curated set of benchmarks, it's very hard to obtain consistent improvements. Specific target tasks are likely to gain from intermediate training, but finding the right source is non-trivial. And in contrast to previous work, I saw no gains from having task heterogeneous batches, as well as actually dataset smoothing. And the best predictor for performance is dataset size for both the source and the target in my setup of uncurated datasets. Thank you for listening, and hopefully see you at the conference. Bye!